Let me see. Say it, 6, 7?
No,
7, 1. Number 75. Has nothing to do with 6, 7, 1. All right. Oh, okay. There is this one idea that I always forget to address. Real quick, just for those of you who are at home, just to remind you. And it's also for me when I look back to make sure what the hell I said it was going to be on. I love taking these videos. It helps me out a lot.
Helps everybody.
Yeah, that's my intent. Even if it didn't help any of you, it helps me out too. I should have wore that one shirt that students take personally when I wear it. I don't know if have you seen that shirt? The blue shirt with Gandalf, and he's standing on the x-axis, and he's like, "Yeah, you shall not pass," because the function looks like this. And I got Gandalf here. You shall not pass. He's got a staff. Right? It's supposed to be his wizard hat. Wait. Beard. Okay. So that's what the shirt looks like. You shall not pass. And what I relate this to be equally geeky. You guys have seen graphs like this before? To be equally geeky, I always think of it instead as it's a trap, and you have to pull up so you don't hit the shield generation, which is to operation. All right. There you go. Something good. Where the shit does this come from? What is in the function? This is a single function that would define this image, except for Gandalf. That function would be very difficult. There's a function that would draw Gandalf, but we're not going to get into there. So this would look something like this. Let's see. Let's say, for example. Because what is that? Let's get a little deeper into this. What x value could I not use in this?
4.
1. Yeah. So don't look at the picture. Look at the function. And I'm going to relate it back to the picture. This is 1. So x equal to 1 would make what happen? Undefined. You doing all right?
Yeah.
What's up? All right. I won't point you at. So x can't be 1, but let's look a little deeper at that. I always forget they put this in the section. It's a beautiful place to put this. Because we know what that undefined, right? But I don't know if any of your professors, I think I said this earlier this semester, some professors call undefined infinite instead. And that's sort of like what this is capturing. Just go up forever. So it makes sense that something really weird is going to happen at 1 on the picture. Why exactly is that weirdness this? We're going to look at real quick right now. So here's something really cool you do later in mathematics. We're going to do it right now. Anytime there's some number I'm not allowed to use, how do I investigate what happens there? I get really close to it. Right? So when I introduce this idea, I always talk about the movie The Blob. You guys ever seen that movie? At the very beginning, I'm talking about the 80s movie. Old man sees this thing hit the ground and gets up really close to it, and he's like, "What the shit's that?" And he makes a mistake of actually getting there. He touches it, it wraps around his arm, he gets eaten. It's horrible, right? But the movie had to start somewhere. So I don't want to get at 1. I don't want to touch it. I can't use 1. It's going to freak it out. So I'm not going to use 1, or else it's going to freak everything out. So I'm going to use something like, what about if we use instead 1.1? That's pretty close to 1, right? What do I get when I put a 1.1 in? 1 over 1.1 minus 1. On the bottom, right? And here's where you guys have to really, really follow me. Let's put together a few things we know. What is 0.1 as a fraction? 1/10. And what is 1 over 1/10? 10. Right? 1 divided by something is reciprocal of that thing, so it just becomes 10. Let me get closer. So guess what I'm going to use now? 1.01. Then I just get a little closer. What is that thing? Get a little bit closer. And when I put a 1 point, are you guys semi with me here? I know 1's weird, so how do I investigate it? Get close to it, but don't go there. So you get 1 over 0.01. If 0.1 is 1/10, 0.01 is 1 hundredths. And what's 1 divided by 1/100ths? 100. So look what's happening. As they get closer to 1, 1.1 goes to 10. 1.01 goes to 100. 1.001 is going to go to freaking 1,000, right? We can see the pattern now. So did you see how that's exactly what happens? Wow. What about the other side? Well, if I put stuff below 1, like 0.9, 0.99, 0.999, that's getting close to 1 from the other side. That's like my friend, hey, Bob, look at this shit. And he's like, oh, he's over there going, what the hell is that? So we're both approaching it, never getting there because we're both smart. I'm not going to touch that shit. I've seen those horror movies, right? Well, me, I would probably just get the hell out of there. I've seen enough horror movies. So if I use 0.9, I really want you guys to get, it's going to be the same thing as this, just negative, because now it's going to be 1 over 0.9 minus 1 is 1 over negative 0.1, so negative 10, negative 100, negative 1,000. Sure. So anytime we have this kind of a wall that the function gets close to but never gets there, that's called an asymptote. Right? Sounds like a math insult. Coming in. Asymptote. I like it. You guys ever heard that word before? You guys? So on this one they say, what's the vertical asymptote? Vertical asymptote. If you get into the next level of math, you actually learn when you have a horizontal asymptote. When you have functions doing this kind of thing. Let me stop there for a minute. Everybody semi with me? So when they say find the vertical asymptotes, that's the exact same question as find the values that make this undefined. If there's a value that makes this undefined, I'm going to put a wall there. You can't go here. I love it. I should have worn that can. I'll have to do it tomorrow. Can't do it tomorrow. I got too many freaking meetings. They'll all glare at me if I'm not, at least casually, easily dressed. Anyway. Oh, screw it. Maybe I'll do it anyway. Yeah. Jeff. Get fired. They're not going to fire me. They fire me for that shit. I don't want to work here. All right. Sorry. I had a lot to process this morning. Is that cool? Is that all right? That's probably more than you really needed. But just remember, they ask you for vertical asymptotes. How do you rephrase that? What x values can I not use? That's where I'm going to put a wall. Yes?
I'm sure this is really simple, and I apologize for asking, but why does 1 over 0.1 equal 10?
Oh, okay. Don't worry. This is beautiful. I don't mean to make it sound like you're supposed to know that automatically. So 0.1 is 1/10, right?
Yes.
How do you divide fractional stuff? There you go. So that's how you get 10.
Sense. Thank you.
That's why I was doing this. So when you divide by fraction, you reciprocate that bottom fraction. So that just becomes a whole number 10. I like it. So when you get closer and it's 100th, then it's 100. And that's why it's going like that and negative on the other side. So if it was this, where would the... What do I have down here today? Is she sleeping? No, she is not. Okay. 1 over x plus 7. Where would the vertical asymptote be? X equal negative 7. Because how do you rephrase that for yourself? What values of x can I not use? So it just gets a little deeper into, all right, you're not allowed to use it, but what the hell happens there then? Or close to there? That's the asymptote idea. It goes one step further. And of course, you're going to get this. What do you got, Jeff? I don't know, man. That's not going to work. There you go, buddy. There you go. So if you got this, what are you going to do? So then you can see the parts. So just to cut to the chase here. Now you have 2 vertical asymptotes at 8, negative 4. I like it. So it would look maybe something like Maybe it even does this thing. You never know. It just has to come up against those. That's one thing it could look like. If you go to pre-calculus, you're going to start graphing these kind of things by hand. And one step is going to be find all your walls, vertical, horizontal. That kind of contains your function. It's neat. All right, so going a little further than you have to worry about for right now. Yes, that's so awesome. Those are really cool. I almost, so if you want to, on your own, if you put this in the graphing calculator, it would actually have a slant asymptote. That's what's called a slant asymptote. So if you graph it, it could look something like, what would it be, Jeff? It's roughly something like this. So then the function could be doing stuff like this. Yeehaw. Now this would have no... All right, I'm going a little further. I'm sorry. Dean's like, man, why did I say that? Does this have any vertical asymptotes? We've seen a bottom like this before. Are there any values of x that would make the bottom 0? Why not? Not just because you can't factor it, but the smallest this could be is 5. Because x squared, the smallest it could be is 0, right? So this would actually have no vertical walls. Okay. Anyway, that's too much. Too much, I'm sorry. But in pre-calculus, you would learn why this situation has a slant asymptote. Anyway, all right. I like it. I like it. See, I love questions like that, but I'm always like, who's getting freaked out right now? Anything else from homework stuff? No? Okay. So let's kind of catch back up to where we left off. We were about to get into what will be everybody's favorite section, the word problem section and stuff like that. What the word problem section is going to do is it's going to have a word problem that ends up with a function like this, or an equation like this. Right, so you have a word problem, you have to set up the equation, you might get an equation like this, and then you solve it. Okay, so the solving part should be the easier part. So how the shit do I solve this thing? What do I do?
Give that one an X, give that one.
Yeah, there you go. Which piece can you break up?
The first one.
Yeah, these other two have nothing else going on. This guy, you can take an X out. So obviously he needs an X. Is it ready? Cool. He needs an X. He needs X plus 12. And then effectively what happens? Bottom's gets a Y. Both sides. It's an equation with two sides, so I'm allowed to do that. I like it. So you multiply both sides by that bottom. Bam, bam, they all die. Like it. Game of Thrones is back on, so it's going to get even more violent, my math. So what do you get? We get x minus 2x. Oh, that was nice. That minus didn't really mess us up too much, because there's nothing to distribute. Equals 5x plus 60. So we get negative x equals 5x plus 60. I'm just going to do it. You guys should all be able to do negative 6x equals 60. So x equals negative 10. Does that freak anything out? What are the only two numbers I had to be careful about? Negative 12 and 0. And we didn't get either one of those, so at least on that level it's okay. It doesn't make the equation undefined. Or go to infinity now, we know that's what it is. So ready? You guys all right? Okay. All right, so that's basically what section 7.6 is, if I remember correctly. Yes. 7.7 is going to be the word problem section. So let's look at a few. One nice thing about this section is there are definite types of word problems you're going to see. And the first word problem is called a work problem. So let me ask you, let me see if you guys get this. If I can mow a lawn in 2 hours, and you can mow a lawn in 2 hours, how long will it take us if we work together? Doesn't that sound, haven't you heard that kind of question before? So I can mow a lawn 2 hours. You do the same thing. Lawn, there you go, John. You also mow in 2 hours. How long will it take us if we work together? So here's.
Wouldn't you divide the work?
Say again?
Wouldn't you divide the work? Like if both of you are doing 2 hours, wouldn't you do 1 hour, I do 1 hour?
In this case, yes. It's really nice when it's equal. In fact, it's even better that it's 2. So I'm starting off really, really nice. After 1 hour, how much lawn would I have mowed? Half a lawn. After 1 hour, you would have mowed. So how long would it take us to mow the whole lawn together? 1 hour. Because we're both working. 1 hour, I mowed half. In that same hour, you've mowed half. Oh, dude, we're done. Yay, we can go home. Wasn't that great? I just mowed the lawn and sorry. You're like, no, it was fast. All right. So you can kind of get a feel for really nice numbers, and you can see how it works. All right. So, but let me show you more generally. So one lawn, I can mow 1 lawn in 2 hours. You can mow 1 lawn in 2 hours. If we work together, we can mow 1 lawn in I don't know how many hours. Now this is a very simple equation to solve. 1/2 plus 1/2 is 1. 1 equals 1 divided by x. Multiply x up, you get x equals 1. So 1 hour later, we're done. But the idea of how to set this up works for any situation. I can do one thing in so many hours. You could do one thing in so many hours. Together, we can do that one thing in I don't know how many hours. And then I can solve for x. Let's try a different problem. Let's say, I can paint a wall in 3 hours. I didn't tell you how long that wall is, so don't give me shit about my painting. I paint a wall in 3 hours. Bob paints the wall in 4 hours because he didn't focus too well. How long will it take us both working together? This equation is really nice. So I can do 1 wall in 3 hours. Bob can do 1 wall in 4 hours. If we work together, we can do 1 wall in I don't know how many hours. And how do you solve that for x? This might look too easy to realize you do the same thing. What does this guy need? And? X. So you give him a 4x. He needs 3x. He needs 12. So then he can multiply by 12x on both sides. I like it. So that dies, and that dies. Let me stop for a second. So work problems are really nice. You through this kind of problems before. Now I have a very good way to just chug through this kind of problems. So what do I get here? 4x plus 3x equals 12. 7x is 12. X is 12 sevenths. Which is about 1.58 something. Nobody's going to help me. That's all right. Is it more than that?
A little.
6.8. 1.68. 6.9? 7. 1.7. So whatever. It's around 1 point something. 1.6 something. Now, real quick. Well, if I got an answer like 5, why is that obviously wrong?
Because it's more than.
It's more than either one of us. The answer I get for it to make sense has to be less than both of us, right? So any answer less than 3 is at least valid in that sense. If you get 10, you're like, what the hell did you put in your equation? The times you guys are talking about Game of Thrones, or you both go off and get lunch. No. Okay, maybe. So let's do one a little bit more difficult. Let me see. Sam takes 3 more hours. Sam is like Rapunzel's cousin or something. Sure, to brush his hair. Then Kim. Like both of these could be girls or boys, or mix and match. Sam takes 3 more hours to brush his hair than Kim. Well, I said it is. Shit. This doesn't really work. To brush his dog's hair. There we go. Give me a break. They can't both work on, I don't know if you guys understand the problem with the way it was. Brush his dog's hair. Then Kim takes to brush his dog's hair. You guys with me? This is like Marmaduke kind of thing going on. Clifford, right? Clifford's the giant one. Okay. There you go. If it takes them what do you got, Jeff? Yeah, sure. 2 hours working together. How long does it take each alone? Let's see if it made a problem that works. So notice how the problems we were doing, I told you exactly how much each, and so that went in there. It's still, this has to be one of us, 1 dog in so many hours, 1 dog in so many. But now what's going to go here is going to be variable expressions. Which one is going to be just x? Same time. Yeah, because Sam takes 3 more hours than Kim. So if Kim is x, Sam is going to be x plus 3. All right, let me stop for a minute. Just because they're unknown now doesn't mean that the fundamental way of putting the equation together changes. It's the same way. So Sam can do 1 dog in x plus 3 hours. Kim can brush 1 dog's hair in x hours. So together they take how many hours to brush 1 dog's hair? 2. There you go. See? So now the variable location has changed. That's all. I know the end, I didn't know what went into it. But the idea of how to put that together didn't change. And now how do I sell that one? That looks a little bit more like what we're used to seeing. What does this guy need? an x, and a 2. So he needs a 2x. He needs a 2 and an x plus 3. And he needs an x and an x plus 3. Now this is where Jeff might have, oh shit, oh well. That's where I need to be more careful. Let's see if I made a problem we can actually solve. Let's find out. So here, so what can I do now?
Times everything by 2x.
Yeah, so multiply everything by 2x, x plus 3 on both sides, so it cancels everywhere. I can only do that if it's an equation. So I have two sides to balance. And then what's left alive again? 2x.
2x plus 6. 1x plus 3. 1x squared.
X squared plus 3.
Yeah. Each pick up another x. Ooh, I might have, maybe. I might have lucked out here. Let's find out. So this is 4x plus 6, right? And then what do I need to do?
Move over
X
the
squared over 4.
I'll go the other way. Keep my x squared term positive, but I need to make this thing equal
0.
0 because I have an x squared term. So I would subtract 4x, subtract 6. Let me see, let me pull up here. So I get 0 equals x squared minus x. Yeah, you totally lucked out, Jeff. All right, no. Pretend I didn't say anything. Oh, I put this thing together. I know it's going to come out.
-3, 2.
Actually, it's still a chance it's not going to work out nice. Yeah, is that cool? Makes -6 and it adds to be -1. So x could either be 3, -2. Which one makes no sense? Physically, yeah. In this case, the -2 doesn't make sense. That would mean I'm done 2 hours before I started, which would be great. You got to do that. It was done 2 hours ago. Holy shit. So throw that one out. Unfortunately, that's not how life works. So what's that mean? 3 hours for Kim. So Kim takes 3 hours alone, and Sam would take 6 hours alone. And the fact that they take 2 hours together makes sense. Okay. So those are nice. That's the worst one of those you would see. And you still set it up. You identify the players, you give them names, and you put them in the right place. This one's always got to be the together. Add these two to make what it is together. So in this case, I just happened to the 2 specifically was how long it took them together. That's why that was a number, not a variable. Okay, I like it. So that's one kind. That's the nice one. Let's do this one. Let's start off with the idea behind this. It sounds good. All right. If you're going, if you have to go 24 more miles, and you're going 60 miles an hour, and you're pretty sure you can hold that 60 miles an hour, what would be your estimate about when you're going to get there? How long it's going to take to get to this place? What would you do? No. So this is interesting because I know you guys have had to do this. Haven't you? You're going somewhere. You're like, I still got this many miles to go. I'm supposed to be there at this time. Am I going to make it? You've done this before. So let's formalize this a little bit. What's the formula that relates distance, rate, and time? Like if I'm going 20 miles an hour for 2 hours, how far do I go? 20 miles an hour for 2 hours. Yes, you would multiply, right? So the distance you go is rate times time. This is good old dirt equation. Right? D-E-R-T. D equals RT. Okay, this is the one we know. But in this situation, what is it that I don't know? What was I asking you about?
How long it's
How long?
so time.
So you want an equation solved for t. How do you solve that equation for t?
You divide D by T.
Solve it for t.
Divide by
Get rid of r. So I'm going to divide by r. I like it. So time is distance divided by rate. So you almost had it right. You just had it upside down. So it's distance divided by rate. So let's see, what is this going to be? So in this case, it's going to be 24 miles. And what's important here is that miles, right? They have to match or else this doesn't make any damn sense. 24 miles divided by 60 mile an hour. Just in case you guys are curious, well, let's finish this number out, and then I want to really show you why the units come out the right way. Stay with me now. What is 24 over 60? How do you reduce that?
Divide by 6.
And actually, to be honest, well,
Or not 12.
oh, go, say again.
Divide by 12.
Yeah, you can divide by 12, sure. So you get 2/5. 2/5 of what?
of a minute, of an hour.
Hours. 2/5 hours. To be. Stay with me. Is everybody decent with that? That's not how you would tell, hey, when are you going to be here? About 2/5 of an hour. Right? I mean, this is not what you can say to somebody. What's really kind of funny here is, does anybody know what's special about 60 mile an hour? 60 miles per hour. How many miles per minute is that? A mile a minute, right? You guys kind of, 60 miles an hour is a mile a minute. So if I'm going 60 mile an hour and I got to go 24 miles, it's going to take 24 minutes. What did we get though? 2/5 of an hour. Well, how long is an hour? How many minutes? 60. 5 goes into 60, 12. 12 times 2 is 24. Get out of there. So we did get 24 minutes, especially if we make this more like a 4. There you go, Jeff. So you've all done calculations related to this equation. You just didn't formalize it to be this equation is what you were using. But I know you've all done it. Right? So that equation is going to govern everything we do for these kind of problems. So here's the kind of problem I'm talking about. Let's say I go hiking and then walking. All right. So I'm hiking through some, not really. I guess you could call it urban hiking. So I'm going at different speeds is the main thing here. Right? So I go hiking and then walking. Let me see. Let me make this. Let me try to make it. Oh, okay. I walk 1 mile an hour faster than I hike. Because I'm hiking up and down mountains or whatever. You with me? Where are you at? All right, now watch. Let me stop here a second. I got to help myself out. I'm trying to make one on the fly, and I got to remember what I need. So here's the way we're going to do this to make this easier. Do you guys see how, obviously in this problem, there's two kind of, you can break the trip up into two things. So in the problems, you'll see like a boat goes upstream and then downstream. So you're going to have 2 rows, upstream, downstream. Here I've got hiking and walking. So really all this chart does for me, to be honest, you don't even need it for real, but it helps you organize what you know and what you don't know. Okay, maybe. Now I just realized, thinking ahead about what it's going to look like, I realized what I can say here to help us out. The total time it took to do this was, let's say, 6 hours. Yeah, okay. How fast was I hiking? How fast was I walking? So let's see, how fast was I hiking and walking? All right. So the main equation behind the idea of this word problem is dirt. D equals RT. That sounded strange. So D equals R times T. So then you start filling this sucker in. Oh, yeah.
It'd be how far was I hiking and walking?
Let's see. No, I want to know how fast. What am I still missing?
Distance.
Yeah, distance. So I'm hiking for 3 miles and walking for 2 miles. Let's see if this works out. I should probably take one out of the book. We'll do one out of the book next. Trying to make these on the fly is a little bit weird. So now watch. So I almost always have to have something to just tell me the number for. They got to give me some definite, concrete information. So that's the 3 miles hiking and the 2 miles walking. So I'll put those in for distance. Now what is it I don't know? I don't know how fast I was going. So how do I represent hike and walk? Which one is going to be just X? So I walk 1 mile an hour faster than I hike. I love it. So if I call hiking X mile an hour, walking would be X plus 1. So I can put those in. So hiking is X, walking is X plus 1. Now here's the big mistake people make. I was trying to force this problem to be this way. I cannot put 6 here or here, right? And I'm not going to put 3 there and 3 there, because then I'm pretending I know more than I do. So what you all, now stay with me. I've actually filled in what I know and what I don't know, and you have these 2 boxes left. What did we just figure out is true about time? If distance is rate times time, time is distance divided by rate. Let's put it there. So what do I put here? What's the distance in this row? 3. And the rate? X. So 3 over X. That's the time. So if I went 3 miles going X mile an hour, how long did it take me? 3 divided by X. Hours. That's what we just figured out with that specific problem over there. I like it. So we do the same thing with unknowns as we do if we knew them. We do the exact same thing. So what goes here? Yeah, 2 is distance over X plus 1. Now, what's true about those 2 things? What's the last thing I haven't used yet? This is the thing that's going to settle my equation.
6 hours.
Took a total of 6 hours. So the time it took to hike plus the time it took to walk better be 6. So the time it took to hike plus the time it took to walk has to be 6. Yes. Oh man, I got myself in trouble again. Well, we'll see. We'll see if I can get lucky twice in a row. I can tap it, but we'll see. Now when I solve this equation, it's the same way we were before. So what's he need? X plus 1. What's he need? X. What's he need? Both of them. He ain't got nothing. Poor little dude. So almost all the time when you do these distance rate time problems, there's going to be a boat going upstream, downstream. There's going to be Sally leaves and then John leaves half an hour later. So that's Sally, John. You're going to have 2 boxes that they just got to give you a number for, 2 boxes that are going to have your variable stuff in, and then the last 2 you get from doing the equation. Distance equals rate times time. So these were blank here, but I knew what time was in terms of distance and rate, so that's how I filled those in. I like it. I know, trust me. Your brain is like, why can't we just stick with shit like that? Because we don't always know all the stuff here. We don't always know everything that went into something. That's where algebra comes in and goes, this is going to be trippy, but if you follow my thing, I'm going to get you the answer. This is how you work backwards. Let's see, what do we have left? So all this stuff dies, because I'm going to multiply by that. Die. So you get
3x plus 3. 2x. 6x squared.
good.
Plus 6x.
Beautiful. This is where I'm really pushing my luck. This is probably where my luck, yeah, my luck's going to run out. Oh, that's too bad for me. But just to go as far as we can, 3x and 2x is 5x, right? Subtract 5x, subtract 3. I need 2 numbers that multiply by negative 18 to add to me 1, but there aren't any. I like it. Some of you guys might know that you could still keep going, we just haven't officially learned it yet. But what would you use here? If you can't factor this, what would you use instead? Anybody know? Starts with Q. Quadratic formula. You guys ever heard of it? Let me just start it off. Negative b plus or minus the square root of b squared minus 4ac over 2a. Does that sound awful? It's okay if it doesn't, because we haven't officially learned it yet. I like it. So let's take a problem out of the book so we don't hit this roadblock. Right? If I'm not careful about the numbers I pick, I'm going to end up with an equation we can't solve yet. We could solve that equation in a few more chapters. We'll be able to solve those equations all day. It's not quite there yet. So let me take one out of the book. That's kind of not satisfying, and I'm sorry. We don't know what the answer is. I love this problem. I don't know if I assigned this one. I don't want to do that one. I want to do... Alright, this is going to be neat. Let's do this one. This is perfect. So this is number 31, in case you have your book, page 566. Man, all my markers are dying. Ah, okay. So 31 says, Destiny's Mercruiser travels... Oh my God, dude. Destiny's Mercruiser travels 15 kilometers per hour in still water. So again, this is number 31. Okay. Mercruiser sounds like it's from Lord of the Rings or something. She motors 140 kilometers downstream. In the same time it takes to go, oh shit, where am I? In the same time it takes to travel 35 kilometers upstream. Holy shit. Okay, stop. Why does that make sense? Yeah, if she's going with the current, she can go a lot further in the same time as against current. This current probably is pretty strong if it's such a huge difference. Are you with me? Or maybe it's a lot of time. I don't know. I think the current's pretty strong. You guys semi with me? You guys get the physical idea behind this? Because it's a little bit easier if you get the physical idea of this. If I'm going with the current downstream with the current, I can go a lot further in the same time as going upstream, against the current. Right? Here I'm going against the current, and this one going, oh yeah, with the current. Probably didn't have to do that, but happened. Well, that just happened. So the weird thing about this is, now they're going to give it away. What's the speed of the river? I mean, that hopefully somebody was like, well, that's the only thing we don't know here is how fast is that current? I was making guesses about it must be pretty fast to make such a huge difference in the amount of distance I can go. So the speed of the river, we'll say speed of current, would be x. That's my unknown. So if I'm going with the current, how fast is that boat going? In still water, it goes 15 by itself. If I'm going with the current, how quick is the current? Beautiful. So if I'm going with the current, it's 15 plus x. So if I'm going downstream, that means the stream is pushing me along with... So if you ever seen kayakers and if they go upstream, they can actually paddle and just stay in the same place? So the speed of the river equals the speed they're going forward, so they look like they're staying in the same place. I guess it's the same thing as a freaking treadmill, when you're walking, like get nowhere. This is great. Get a old screen and have some freaking nature on that sucker. That's right. You guys semi with me? Okay, so let's put this thing together. I think you start to see how this variable comes into play. What are these two situations? Upstream and downstream. I like it. So then you got distance, rate, time. What is it I know for sure? This. So downstream, it's 140. Upstream is 35. How fast was it going downstream with the current? It goes 15. And if it goes with the current, plus the current speed. If I'm going against the current, it's going to be 15 minus x. And you can imagine the biggest mistake is people turn that the wrong way around. But that doesn't make any sense. So if I was in a boat that was going 15 kilometers an hour and the current was going 15 kilometers an hour, that boat would be sitting there stationary. They're like, it's going to take a long time. How long? Infinite amount of time until we get there. Okay, I like it. Same way we feel on the highways, right? If you do enough of these problems, you start to realize, what's going to go in there. It's going to be the division of those two. Time is distance divided by rate. So distance over rate. Distance over rate. Now here's the real tricky thing. What the shit is the equation? What ties this together? It's one small phrase. It's so easy to miss. Nope.
Same time.
Same time. So whatever that is, has to equal this. That's the equation I'm going to use. And this is good this is coming up because somehow I missed talking about this, but this is the one place you can do a certain thing, which is a shortcut. So let me do this the long way, so nobody yell at me about, why are you doing it that way? And then I'll explain why the shortcut works. What's this guy missing that he's got? 15 plus x. What's he missing he's got? So then I can cancel those out. So what's it look like happened? It looks like that came up here and that came up here. Cross multiply. Cross multiplication is just a shortcut to the way we would do it anyway. So if you have any trouble with cross multiplication, just screw cross multiplication. Just do it the way we do anyway. Doesn't even save that much time. So now you got the beautiful thing about multiplying this stuff in. I'm gonna say this, and if you get this, this is really kick-ass. I would divide both sides and decrease the size of those numbers first. What goes into 140 that also goes into 35? And 7. So the whole 35 goes into 140. Wow, 35 times what is 140? Yeah, all right. Let's do it the long way. Because you might not notice this. So what do you do here? You just multiply this through. What's 35 times 15? I don't know. Was it 575? 525? Plus 35x. And then distribute this. 30 times 70 is 2100. Yeah, 2100 minus 140x. Real quick. I'm sorry. Side note. To do 140 times 15, I doubled 15 to make it 30, and then I cut 140 in half. The product's going to come out the same because I just balanced it back out. So whenever I have an even number times something that would have been nicer if it was double that, you could do this. Or, you get the calculator. All right. So now we add the 140. We subtract the 525. What is that, 1575, I think? And then we hope that those go in. Is everybody kind of with me? I mean, this equation is beautiful compared to some of the ones we've seen before, right? There's no x squares. So I can just add 140x, bam. Subtract 525, bam. And then divide by 175. And whatever the hell that is. 9? 9? Okay. 9. So relative to the boat, that current is pretty strong. It's 9 kilometers an hour, and the boat goes 15. I think, what's the question again? 30. You always want to make sure. This is the last step. What is the speed of the river? Cool. So 9 what? Kilometers per hour. I like it. That's not American. I know. You know how many countries don't use metric system?
Everyone but us.
Don't use metric, just us.
Just us.
Used to be 3 countries, but the other 2 woke up. And America just keep on. Anyway, sorry.
How else would we know what a quarter pounder is?
Royale cheese.